Welcome back, everybody. Now we are going to focus on the PowerPoint, which is titled Kinetics. In this presentation, we are going to talk about force and torque and mass and weight. So we have to be well familiar and versed what is what and what is this all about. So what is force? Well, force is used either to push or to pull. Why do we need that force? Of course, to produce, stop, or modify the movement. So again, the force is used to produce, stop, or modify the movement. We have a mathematical formula which is F equals to m multiplied by a. Of course, F stands for force, where m stands for mass and a stands for acceleration. And we will talk about force equals mass multiplied by acceleration a little bit more in this presentation, but also in the future video. Okay, so let's go to the next slide. And in the next slide, we have to understand and distinguish between what is weight and what is mass, to understand that all throughout the human history, until Newton, we didn't know that there is a difference between weight and mass. We didn't even know that such a thing, that we can even distinguish those, that even is a question. Mass and weight was absolutely interchangeably changed, and if you knew what is weight, you knew what is mass, and vice versa. Well, Newton changed that. After Newton, physicists, mathematicians, biologists, all the science people start to understand that mass and weight is not the same. So, in other words, what is heavy and what is massive? Well, let me see if I have some more. Okay, here. Let's go to the next slide. The weight of the body is a gravitational force exerted on a body by the earth. Okay, so let's talk about this just a little bit. Weight, it's not a mass. Mass is internal when weight is external. What do I mean by this, internal, external? Well, mass is, let's say, the total number of cells in the body, or the total number of cells in any other object. It's internal. You don't change that. You are in the moon, on the moon, you are here on Earth, you are someplace else in the universe. The number of cells do not change. However, weight is a force. What type of force? Gravitational force. So two elements actually are going to be very influential on the weight: mass and gravity. The more massive you are, or the object is, and the more or greater gravitational pull, the more weight. So it's directly related to the force of gravity. So by definition, weight is not static. Mass is static. Weight can change. And let's take into consideration the second point in that slide. For example, weight of the body changes on the south and north poles as compared to equator. Weight of a body changes on the moon. Okay, let's talk a little bit about that. Earth is not perfectly sphered. It's not perfectly round. It's a little bit squished. You don't really readily see it in the naked eye, but it is. So the poles are a little bit closer to each other as opposed to the two ends. I'm looking for the camera. Two ends of the equator, right? So anybody, your body, physical body, or any object would weight differently in different parts of the world. So your weight would be less on the poles and more on the equator. Similarly in the moon or any other celestial object. Moon is approximately 6 times less massive than Earth. What does this mean? That means that the gravity is significantly less on the moon as opposed to on Earth. And you can clearly see this by observing astronauts walking on the moon. Did they get any stronger on the moon? Absolutely not. Their muscles produce the same amount of force. However, because the gravitational pull is less on the moon as opposed to on Earth, every step they take is significantly bigger. It almost look like they jumping from one foot to the other. Okay? In other words, weight is a force and should be expressed in force units. What is a force unit? Newton. In physics, it's called Newton. 1 Newton would be a description of a force. Now, weight cannot or should not be really expressed in kilograms or pounds, but it is. Again, in physics or in mathematics, that would not be appropriate, but in everyday life on Earth, it is. Why? Let's take a look at the next slide. The mass of the body, on the other hand, does not change wherever you are, on Earth or any other place in the universe. Mass, like I mentioned before, is the number of cells. It is the sum of your parts, so to speak. So it doesn't change no matter where you are. That's your mass. So in other words, mass is internal. When force or weight, it's an external force produced by gravitational pull. But like I mentioned, don't worry, on Earth those differences are so small. Then for everyday use, we can interchangeably use those descriptions. Either it's going to be weight or a mass. Doesn't make that much of a difference. So it's safe to use it interchangeably. But just so you know, that in physics, this would not be acceptable. All right, let's go to the next slide. This is just a fun fact. Not going to ask you for that. Challenge. What is the mass of the planet Earth? Where that was calculated, there is a method of calculating, mathematical method of calculating the size and the weight and the mass of celestial objects. So the physicist calculated, and I can't even tell you the name of that because it has way too many zeros, like 6 whatever kilograms. Now 1 kilogram is approximately 2.2 pounds. So multiply that number by 2.2 and you're gonna have even larger number in pounds. Okay, this is just a fun fact. Let's go to the next slide. Okay, so let's talk about scalar and vector quantities. What is this all about? Scalar quantity, think about, can be measured using by scale. If you can put something on scale or use some type of scale, that means that the quantity is static. So have a magnitude but magnitude only. So examples are time, space, and mass. It has a magnitude, but really no direction of movement. Vector, let's go to the next slide. Vector quantities, however, indicate movement. Therefore, they are constantly changing. So can be measured only in a very specific point of time. So it has not only magnitude, but this time has also direction. So you can't simply put that on some type of scale, because the scale is not going to give you a direction. It's just going to give you a magnitude. All right? So let's go to the next slide. Tug of War. Tug of War. So we are talking here about newtons. So you can clearly see that the weight of that person on the far left is 500 newtons. Well, because the weight is expressed in the correct form, which is Newton, 500 newtons. The next person is 200 newtons, and to the other side of that rope you got 100 newton, 400 newtons, and 300 newtons. So this can be of course calculated in very precise way, and you do not have to memorize this. I won't give you any examples to calculate this, but just for your own sake, what is 1 newton, or how can we mathematically express 1 newton? Well, 1 newton equals 1 kilogram, and if you want in pounds, 1 kilogram again is 2.2 pounds, multiplied by 1 meter divided by 1 second squared. So it's a little bit complicated formula, and it's mathematically possible, of course, to convert newtons into kilograms, and then kilograms into pounds. So we're not gonna do that much, and we're not gonna go that deeply into mathematics and physics. But just by looking at it, who do you think is going to win this war? The left side or the right side? And clearly, you know that the right side is going to win, because the left side produces 700 newtons of weight, and the right side produces 800 newtons. So just by looking at the numbers, you know who is going to win. So is this would be this action, this tug of war, would be considered scalar quantity or vector quantity? Clearly we can see that it's a vector quantity, because we're not only dealing with magnitude, which are the weights of those individual people, but also direction of application of that weight and their force. Okay, let's go to the next slide. Types of motions, we already talked about that in the previous videos, so just a quick reminder really, that we got translation or linear objects. We're talking about straight line. So if you're pushing an object from point A to point B, that's a linear or a translational movement. So all points of the object move in the same direction at the same speed. They are making the same distance at precisely the same time, because if any one of this would be distorted or different, you would rip the object apart. Okay? Rotational, that's how our body moves, that's how we move. So so rotation, it can also be described as a axial or angular movement, right? So one point of the object is fixed, and the remainder of the object moves in an arc around a fixed point. And I gave you this example already, but let's take a look one more time. This is axis of rotation of my elbow. It's stationary, doesn't move, but my forearm goes, and you can see my fist clearly in the circular motion. It's a part of an entire circle. right? So it's angular or axial or rotational. This all means the same thing. All right, let's go to the next slide. System of leverages. That's how our body works. That's what we do in order to move. So it's very important for us to understand the process of how we move, and therefore the leverages. So let's talk about them a little bit more in depth. Just bear with me. Lever is a rigid bar or structure that turns around fixed point, representing the bones of the body, which we already discussed in the case of my elbow. Fulcrum is a fixed point around which the rest of the bar moves, representing a joint, axis of rotation, and each joint has a very specific axis of rotation, which we will know by name, and we will learn how to palpate, how to find it for the purpose of goniometry and manual muscle testing once I see you in person on campus. Force is usually representative of a muscle, and resistance is everything what actually fights against that muscle force. Therefore, could be external resistance, such as weights or therapies applying resistance, or gravity. Gravity by itself is considered resistance, and we talked about that already with the manual muscle testing video when we talk about the scale 5/5, right, or 0/5 and everything in between. We talk about how important the gravity is, because gravity is an external resistance. It creates a force, which we're gonna call it in this case resistance, and the force we're gonna call the force which is created by muscles. Okay, let's go to the next slide. So we got force. It's of course labeled F. We already know that. Resistance is gonna be labeled R. Force arm, and this is a little bit confusing perhaps, but I want you to understand because it is used interchangeably, and depending on the source you're going to read, the books and articles, those terms are used interchangeably. So force arm is also called internal moment arm. Why moment? Because always changes, because as it changes as fast and as quickly as we move. We move, a moment arm changes. Why is called force or internal? Remember what we just said, force is created by muscles. Internal moment arm, that word internal means the distance between the fulcrum or the axis of rotation of the joint and the tendon of the muscle, therefore is internal. Or force, so force arm equals internal moment arm, used interchangeably. Resistance arm, distance between the point of resistance and the fulcrum, labeled RA. It's also known as external moment arm. Why external? Because the force applied to resist, or the resistance applied, which is of course in the form of a force, but I want you to just distinguish between those two. So the resistance is applied as an external force, meaning therapists can apply external force or resistance, some weights, or gravity. Okay, so again we got kind of like double name, but bear with me, it's not really that confusing. You just have to get used to it. Okay, torque. What is torque? Torque is considered a rotoric equivalent of a force. Okay, so to be a little bit even more confusing, hopefully clarify that confusion. Force is it's usually if we're talking about force created by muscles, this force is linear. Muscles can only work in a straight line. Muscle cannot perform any type of this kind of motions. The bones do, but the muscles do not. Okay, so depending how the muscle wraps around the bone and where attaches to the bone is going to behave perhaps differently. But the belly of the muscle, the working horses of the muscles, they cannot produce anything but straight contracture, okay, of the muscle. So torque is considered a rotary equivalent of the force. So if you see the word torque, it means force, but instead of straightforward force, it's going to rotate. Okay, so how do we produce the torque? The torque actually is produced by leverage, the leverages or levers. Moves around a fixed point to rotate and makes an arc of or a circle. So torque equals force multiplied by force arm, or force multiplied by internal moment arm. Just like I mentioned before, we can use it interchangeably. Or the torque or the rotary motion can go into the opposite direction, meaning towards the resistance. So then how we calculate the torque? Well, it's resistance multiplied by resistance arm, or resistance multiplied by the external moment arm, which again, those names can be used interchangeably. And of course, the correct measurement would be Newton to meters or foot to pounds, and that would be most physics and mathematics would use that formula. Of course, we are going to modify this to our needs, and we're going to talk about pounds. So let's go to the next slide. And we are starting to talk about those levers in our body. Our body uses three types of leverages, or those levers. First class, second class, and third class, and we are going to discuss all three of them. So fulcrum is between the force and the resistance. Imagine the seesaw. In our body example, atlanto-occipital joint, head and neck. This is from our body. But let's take a look at the next slide. And this is a graphic representation now. Fulcrum, you can clearly see, is represented by this white triangle. On your left hand side, you're gonna see force, and meaning the tendon of the muscle is represented by this white arrow, and the white arrow on the right hand side is it's a resistance, and the resistance could be, of course, weight, could be gravity. And FARA stands, of course, for force arm, and RA stands for resistance arm. So you can clearly see that they are in equilibrium. The length is the same, therefore the force and the resistance is the same, because the seesaw is in complete equilibrium. All right, let's go to the next slide. You can see a seesaw here in more realistic picture or drawing. You have that again seesaw device, and you have that fulcrum represented by this big triangle, gray triangle on your screen. On the left hand side we have a boy, and on the right hand side we have, let's say, for argument's sake, his father. So how come the seesaw is in equilibrium? Nobody is higher, nobody is lower. The boy is as high as the father, and there is no motion. It's very static. Okay, let's take a look at that. Let's say, for argument's sake, you can play with numbers, different numbers, but let's say for argument's sake that the boy weighs 75 pounds. And let's say for argument's sake that the gentleman weighs 150 pounds. Let's say that the distance between the gentleman and the fulcrum let's say, is 3 feet. So we don't know how far the boy needs to be in order to keep that device in equilibrium. But actually, I gave you those numbers because they are very easy to calculate. You can play with other numbers. The boy was 75 pounds, his father is 150 pounds, therefore the father is twice as massive as the boy. Therefore the distance between the boy and the fulcrum must be twice as long to contradict the extra weight of his father. And clearly, if the distance between the father and the fulcrum is 3 feet, then between the boy and the fulcrum must be 6 feet. Okay, let's go to the next slide. Okay, this is the example I gave you before. So this is the head and neck, first class lever. So clearly you can see that between IMA and here we are, the authors changed the terminology on us. So IMA, internal moment arm, and EMA, external moment arm, or force arm and resistance arm, used interchangeably. So please don't get confused. So what are we looking at over here? The fulcrum, as you can see, is that dot in the center of the connection between the neck and the skull. On the left side, you have that red arrow, which represent the muscles, the neck muscles, or more specifically, the tendon of the neck muscles. So the distance between the tendon of the neck muscles and the fulcrum is internal moment arm. Again, why internal? Because it's inside between muscle and the fulcrum. What in this case is external? Well, the weight or the force of the skull, we can use it interchangeably, so I'm just gonna, for easiness of speech, I'm just gonna refer to as a weight. So the weight of the skull is going to be the external resistance or the external force causing resistance. Why external? Because our internal muscles must work hard to prevent our skull, therefore our entire head, to go down. Instead, so to prevent that, our muscles have to pull back. So depending, of course, how much the skull weighs or what you have actually on the head, that much the muscles needs to work. So in this case, it was already calculated for us the correct way with newtons, and then calculated mathematically. Formula was utilized and converted to pounds for easiness of use. So muscle force, or MF, is unknown, we don't know it, but we do want to know that. Head weight is 10.5 pounds. Internal moment arm is given to us is 4 centimeters. External moment arm is given to us as 3.2 centimeters. Don't worry about the mechanical advantage. We're not going to talk about that. I don't want too much confusion about that. So let's just keep it simple to what we need to know. So we're going to add our formula to it, which is MF multiplied by IMA equals HW multiplied by EMA. And of course, MF stands for muscle force. You can simply just say F as a force. And HW, it's a head weight, which simply could be referred as R, or resistance. Everything is calculated, as you can see, and we end up with 8.4 pounds. So muscle needs to produce 8.4 pounds of force in order to contra the head, which weighs 10.5 pounds. So the muscles in this case needs to work a little bit less than the resistance they actually fighting with. Okay, let's go to the next slide. Second class lever. In this case, force and resistance are on the same side of the fulcrum, with the resistance between the fulcrum and the force. In everyday life, we can use the bottle opener as an example. In our body, our foot, when you're standing on your toes, you're utilizing second class lever. Let's take a look at that. Let's go to the another slide. This is a graphical representation of what we are discussing. So you got your fulcrum on the far left, then you have resistance, and after the resistance comes force, which is of course a little bit different here. So let's go to the next slide, which I'll be able to show you on human body, and we will understand this a little bit better perhaps. Okay, so this is exactly what we utilizing in our body. As you can see, it's not often occurrences. We are not using the second class lever perhaps as much, but nevertheless it's there, and it's important to know it. In the everyday objects or activities, you can see on the left hand side the wheelbarrow, we are using the same concept. So let's take a look at the picture first. So you can see clearly the white dot, as long as I can see it, it's a white dot with the black rim around it, which represent the fulcrum or the axis of rotation. The external moment arm is very short, and it goes to the BW, which stands for body weight, or we can simply say R for resistance. And where are the muscles? The muscles are way behind it, way behind it. Those are our calf muscles. So the internal moment arm or the resistance arm is much longer in this case, but they are on the same side when the fulcrum is on the opposite side. And again, you can take a look at those numbers. Muscle force, how much force muscle needs to generate, knowing that the body weighs 150 pounds, internal moment arm is 12 centimeters, and external moment arm is 3 centimeters. Again, mechanical advantage, we don't have to be worried about that now. You put the formula to work, and you end up with 37.5 pounds. So in order to generate enough force to contradict the body weight, muscles needs to work not as much, only 37.5 pounds, and they are able to lift and sustain a body which weighs 150 pounds. So the mechanical advantage actually it's pretty good. Okay, so let's go to the next slide. The third class lever. Well, let's take a look. Force and resistance are on the same side of the fulcrum, with the force between the fulcrum and the resistance. Most levers in the body are third class levers, and that makes sense. Remember what we said before, is either stability or mobility. The other two levers were more advantageous because they were more designed for stability rather than for mobility. But it's one or the other. It's always something for something, right? There is never a free dinner, so or free lunch. So what are we losing here? We're losing that ratio. The muscle needs to produce much more than we're getting in return. But on the flip side, this allowed us to move So let's take a deeper look at that. I'm gonna go to another slide, and again this is just a graphical representation. So on the very left hand side you got that fulcrum, or the center of the joint. On the right hand side you got both force, muscle tendon, or force produced by muscles, and resistance, meaning weight, external weight, and gravity. So they are on the same side, but now reversed, as opposed to second class lever. Remember the second class lever? Look kind of like that, but force and resistance was reversed. Okay, let's go to the next slide, and you can clearly see third class lever is used for movement. But let's take a look at this composition and this ratio of work versus payout, so to speak. So muscle force again is unknown. External weight is 15 pounds. So let's say that dumbbell is 15 pounds. Internal moment arm is 5 centimeters. So again, this is the distance from the elbow to the tendon of the muscle. That's the internal moment arm. External moment arm is 35 centimeters. That's the distance from the elbow to the weight. It's put into the calculation, and we end up with 105 pounds. And pay attention that the formula never changed. It's always the same. So you know this formula, you pretty much good to go. 105 pounds. Let's take a deeper look at those numbers. In order to lift 15 pounds of weight, your muscle needs to produce 105 pounds worth of internal force. Is this a good payout? Not in my book, but we can move something for something. Okay, so let's go to the another slide. Mechanical advantage, I didn't talk about that much, but let's just cover very mildly. Efficiency of the lever. How efficient is the lever? So efficient when a small force required to overcome a large resistance. Makes sense. Somebody or something gives us a lot of resistance, and we need to work a little bit in order to contradict that. Is this advantageous to us? Absolutely. So the calculation is extremely easy actually. It's mechanical advantage equals force arm divided by resistance arm. Those numbers are given to you during those calculations, or you can measure yourself if you're interested, of course. And the general rule is that the force arm is greater than resistance arm, then the MA is greater than 1. In the third class lever, MA is always less than 1. So let's put this in more understandable terms. If the number is 1 or more, this is a great advantage for our muscles. The bigger the number, the less work our muscle needs to do in order to contradict any given resistance. But if it's less than 1, let's say 5.44, that's horrible for our muscles. That means that our muscles have to work a lot to contradict that resistance. Okay, and you can clearly see that in the third class lever, the example I gave you, the mechanical advantage is 0.143, way below 1. Therefore, that's why you have to produce 105 pounds in order to just contradict 15 pounds of resistance. This is a huge disadvantage for our muscles. All right, but again, something for something, either stability or mobility. So if mechanical advantage is greater than 1, then of course the lever was built for force. And if the mechanical advantage is less than 1, was built for speed. Or think about also stability versus mobility. Okay, you are more stable when the mechanical advantage is greater, and you are less stable when the mechanical advantage is less than 1. Okay. So the next one, it gives you the same formula we saw already several times, and again you can use Fa as a force arm, is an internal moment arm, and Ra as a resistance arm, as an external moment arm, interchangeably. The formula is identical. Okay, so this is just a very simple examples. We can take a look at that. Very simple calculations, so don't be afraid to use different numbers, just to check yourself, just to challenge yourself. So first question is, what class of lever are we looking at? Where you can clearly have a resistance on one side, actually two resistances in this case, and the force on the other side of the fulcrum. Clearly this is first class or the of lever. Okay, so we have certain numbers here given to us, right? So let's take a quick look at this. Resistance 1 and resistance 2. Resistance 1 is 9 pounds, resistance 2 is 1 pound, and the distance from resistance 1 to the fulcrum is 1 inch, and resistance or foot, and resistance second is, you tell me, it's 3 feet. Because you have to add 2 to 1, because we're going straight to the fulcrum or axis of rotation. So 2 plus 1 is 3. And the distance between force and fulcrum is also 3 feet, which apparently that doesn't really represent well, because those distances should be kind of looking even if 1 plus 2 is 3 and then on the other side is 3, but somehow you can see it's much shorter. So I think this is overlooked by the authors of the book. But nevertheless, how we can calculate this? Well, the same way, but we have to calculate for two resistances separately, and then add them together. I'm going to do that on the paper, and I'm going to show you, so we have exactly understanding of where we are. So let me do this calculation for you right here very quickly. Okay, so let me try to show you this calculation. So this is the formula: MF times IMA equals R multiplied by EMA. So we can pull the MF out, right? The muscle force, or the force. That's the question. So we're gonna pull it out. MF, muscle force, or just force, equals R multiplied by EMA divided by IMA. So we have to do this in two separate ways, because we have two resistances. So resistance 1 was given to us as 9 pounds. What's the distance? 1 foot divided by IMA, which is 3 feet. So we end up with 3. Let's calculate this now to the second resistance. We have 1 pound multiplied by distance. 2 plus 1 is 3. So divided by the distance on the force distance is also 3. So we end up with 1. What we have to do, we have to add those two. 3 plus 1 is 4 pounds. So again, just so you see it, this is the formula. I pull out the MF or muscle force, and this is the calculations. We have to add it up, is 4 pounds. Okay, so now, is this advantages or disadvantage? Well, I think this is a great advantage, right? Because we calculated just now that muscle have to produce 4 pounds in order to keep in equilibrium or contradict two different resistances at once. One was worth 9 pounds, the other was worth 1 pound. Okay, let's go to another slide. Okay, what class of lever is this? This is a second class of lever because resistance and force is on the same side, and fulcrum is on the other side, and we have some numbers here, right? So resistance is 6 pounds and the internal moment arm is 9 feet, and the force is unknown, and the distance is 9 feet or 9 inches, whatever is your pleasure. What are we going to do with this? We're going to put this in exactly the same formula, and let me calculate this for you very quickly. So the formula doesn't change. Okay, so again, the formula doesn't change, but is very simple, much simpler than the example before, because we have only one resistance. So force or muscle force equals resistance multiplied by external moment arm divided by the internal moment arm. So muscle force equals the number is given to us 6, the distance between the resistance and the distance, the external moment arm is 9 divided by the distance from force to fulcrum, which is 9 plus 9, as you can see on the drawing. That's 18. So 54 divided by 18, that's 3 pounds. All right, so we got that down. So 3 pounds, is this advantage or disadvantage? It is advantages because the resistance was 6 and we needed to produce only half of that to keep it in equilibrium. All right, let's go to the next. What class of lever is this? This is of course the third class of lever, and very similarly we can calculate this using the same formula. So you got force. We don't know how much force we need to utilize or produce in order to contra the resistance worth of 5 pounds. The distance or the external moment arm, it's 5 plus 5, which is 10, and the force arm or the internal moment arm is 5. So we're gonna put to the same formula. You do it yourself, and you should end up with 10 pounds. 10 pounds. You should end up with 10 pounds. So now the question is this advantageous? No, it's not, because the resistance was only 5, but we needed to produce 10 pounds worth of force through our muscles in order to contradict only 5 pounds. So we are in the deep disadvantage. However, we can move. We have to produce more force, but we can move that resistance towards our advantage, whatever it is, bringing something to your mouth or whatever it is. Okay, let's go to the next slide. So we already talked about that. I already give you some information about that. So two types of musculoskeletal torque. Remember, the torque is a rotary equivalent of force. Force is linear, torque is rotary. So external is outside of the body, and internal is produced by muscle. Again, the muscle cannot produce or create torque by itself. Because torque is rotary. Muscle can only do it in the straight line. Remember, just contract, relax, contract, relax, contract, relax. So no rotation, but they create rotation through tendons which are smartly inserted into our bones. Okay, let's go to the next slide. So this is another representation of internal torque and external torque. So as you can clearly see with the red arrow running through the biceps produces force. So it's internal force. This internal force produces internal torque. The force produces torque. The torque is rotation. So this particular person on this drawing, when applied the force produced by muscle, will bring the forearm up. Forearm up. So this would be internal torque because it's produced by internal muscle. Now external torque would be the opposite. I'm going to have something heavy in my hand and it's too heavy for me, therefore it's forcing me to go down because I'm too weak to hold it. Therefore it's going to produce external torque. So external force or resistance is going to create external torque. So as you can see that the external torque is always clockwise, always, and internal torque is always counterclockwise, and you can see it on this picture. Okay, let's go to the next slide. Lever moment arm, we already talked about that. So is the radius of the specific arc of motion. This line runs perpendicular from one line of force to the axis of rotation. The moment arm or torque arm changes as the muscle contract and lengthen. We already talked about that extensively, but let's take a look at the drawing one more time just to make sure that we're on the same page. So here we are, moment arm. Again, why is moment? Because momentarily changes as quickly as you can move. The moment you move, the moment arm will change. So in a case of an elbow, and this is in the case of an elbow only, every joint, every part of the body has its unique characteristics. But in the case of elbow, when the elbow has the most potential, well, elbow has the most potential in this position, 90 degrees. Why? Because only from 90 degrees flexion you can go the same amount, you can cover the same amount of distance either towards flexion or towards extension. If your elbow is more extended than 90 degrees, then you have more flexion but very little extension. And to the contrary, if your elbow is more flexed than extend, then you have a lot of extension but limited flexion. So we're gonna call elbow, for the elbow position, 90 degrees of flexion gives the most rotary or torque abilities. And you can clearly see that concept on this slide with the arm and moment arms. So the red dotted line represents the forearm in 90 degrees to the arm. Forearm and arm in 90 degrees or approximately 90 degrees, and you see that dotted red line. This line is the longest when the elbow is at 90 degrees. Everything else, what what is either more towards flexion and or more towards extension will shorten that moment arm. So the moment arm for the elbow is the longest when the elbow is at 90 degrees, and that position is the most advantageous for our elbow because we can evenly distribute extension and flexion. I hope that I'm making any sense here. Okay, let's go to the next one. And why this is important? Why did we cover just this information about the elbow? And why do I bother? Why do you need to know this? Well, this next slide, it's called changing resistance arm. It's a perfect depiction of why this concept is important. Like I mentioned, similarly to elbow, any other joint of your body will produce similar results when you have most advantageous position or most disadvantaged position of the particular joint. So let's take into consideration this picture over here with the drawing of a man who lifts 10 pounds of external weight, or he has 10 pounds worth of resistance when his arm is 24 inches in length. So take into consideration the middle of his shoulder to his wrist, middle of the wrist, where he actually, not the wrist, I'm sorry, the fist, when he actually holds the dumbbell. The distance is 24 inches. So this is the length of his arm. So this is also mathematical calculation over here. That's funny looking R represent radius. So this is abbreviation for radius, and radius equals force multiplied by distance. So you have over here different examples. So you got radius at 60, 90, and 150 degrees. So the same 10 pounds and the same length of the arm. Let's see where this person is in the most disadvantaged position and the best position to hold just 10 pounds. And what's going on in his body? Well, the same 10 pounds multiply by 24 inches, the number in between, when he holds actually at 90 degrees, he needs to produce, his muscle needs to produce 240 pounds just to keep that weight in equilibrium. If he goes down to 60 degrees, the first number, you multiply 10 pounds by 20 inches this time, because that's the distance from his shoulder to the weight, if you are drawing the straight line, and that gives you 200 pounds. And when he goes all the way up to 150 degrees, for example, multiply by 12 inches this time, because that's the distance from the dumbbell to the middle of his shoulder with a straight line, and that gives him 120 pounds. So you can clearly see that the weight farther away from the body, the more work must be done by muscles. Very important concept for us as therapists, because that's what we teach our patients. Hold the weight close to the midline, hold the pad close, hold the suitcase close. Never lean forward and try to lift anything. You're going to damage your muscles, your joints. This is not according to correct body mechanics. So it's a very, very important concept to understand this particular slide. Okay, let's go to the next slide. Isometric contraction, and the next slide is isotonic contraction. We already covered that in the previous presentation. We already covered a couple of slides. The last two slides is how forces are applied to musculoskeletal system. tension, compression, bending, shear, torsion, and combined loading. And the last is showing you how those forces can interfere or compress your muscles. I hope you enjoyed this lecture.